is a group leader right now at Tübingen. Before that, she spent some productive years at Google DeepMind in the UK. Claire's research focuses on the foundations of sequential decision making, which includes, say, bandit problems and RL. Her work has received a number of awards, including, for example, the iClear Outstanding Paper Award a few years ago, as well as grants including the ERC Starting Grant and the Another Award. Beyond her excellent research, she's also done a lot of service to the learning theory community, including being program chair for Alt last year, as well as the co-founder of the iClear blog post track, which I think is a really nice addition to that. And beyond that, also helping foster a community and mentorship for women in machine learning theory, which I also think is important. So without further ado, I'll pass it off to Claire.
Thank you. All right, is this working? Like, can you hear me well? Okay, great. All right, so thank you so much for the kind introduction and for the invitation. It's always a pleasure to come to ALT. And yeah, today I'm going to talk about risk-sensitive optimization in Markov decision processes. This is a work that is the fruit of a 2-year collaboration with my colleague Aurélien Garivier and our joint students, Alexandre Marthe from ENS Lyon, whom you might meet if you come to COLT this summer. So I noticed that there aren't that many RL talks at this conference this year, so I tried to make the content of this talk accessible to all. So we're going to start with a small game together. So assume that we are going to be the owner of a pop-up bike retail store in Milan for the next 20 weeks. And every Monday, at the beginning of the day, we can observe our stock. We start with 10 bikes in our little store. And every Monday, we observe our stock, ST. And what we want to do is decide how many bikes we should buy for the rest of the week. So that's our action, AT. And this is going to be our total stock, ST plus AT. And yes, and this total stock should not exceed our maximal storage capacity, M. And okay, so there is going to be customers coming. So our customers' demand is modeled by this like random variable, this binomial random variable that has quite some variance, right? So across the days, there are more or less customers that are going to come to the store. And our revenue at the end of the week is RT, which is like how many bikes we've sold. But we cannot sell more bikes than what we have in storage, right, for a week. The profit at the end is the revenue minus the cost of storage and the cost of buying the bikes at the beginning of the week. I did assume that the bikes come right away, so it's a local provider of bikes, right? So like when you order the bikes on Monday before opening, they arrive on time for your week. Okay, so the problem of the store manager is to order enough bikes to mitigate the risks of not having enough in your store, so that when the customers come, you know, like you want to sell as many bikes as possible, but you also want to kind of not have too much storage costs. So there's a bit of like kind of risk trading with like, yeah, we understand the problem. Okay, cool. So there's essentially 2 types of strategy. So it's a very well-studied problem in operations research and in finance. Like essentially, the optimal or the type of strategies that are going to solve the problem is known, but like you can think of it as like there are 2 different types of strategies. There's the conservative manager who's going to say, I'm happy to like have some moderate storage at any time. So I lose a little bit. Like if there are too many customers, I'm gonna sell everything and I'm not gonna have enough for everyone. But in the meantime, I'm saving on storage costs. So I'm conservative in that sense. I'm not, you know, overspending, but also not overspending on storage, but not over like estimating the demand. On the other hand, there's the YOLO kind of manager who is saying, okay, let's just refill to almost, you know, full capacity or like very high capacity, so that whatever is the demand, I can sell all my bikes and I make like large revenue, right? But like I pay a lot of storage if there are no customers. So my risk here, the risk factor, is the demand, the fact that there's variance in the demand in the customer's variable. So I simulated this little game for you. I made 1,000 simulations with the 2 different behaviors that I just described. So the risky behavior, the blue behavior. gives you this kind of revenue. So essentially kind of large tail, you know, like if the demand is great, if there is a good, like, I don't know, if the demand has a high value sometimes, you're just going to sell a lot of bikes and you're going to make large revenue. But on the other hand, if you're unlucky with the demand, then you're going to have like losses. And the conservative behavior leads to a much more concentrated kind of revenue distribution. And these two distributions have roughly the same expectation, which is this black dot in the middle. But what they have different is this value at risk, or the quantile. And so it's quite visible on these curves, right? The quantile of this distribution are different. And this is often referred to as the value at risk in finance, which is essentially like the quantile, right? Like the value at risk is the quantile for a certain alpha that you set. Most of the time, people actually look at the conditional value at risk, which is the expectation conditionally that you're in this quantile kind of interval here. Okay, so this type of metrics, value at risk, conditional value at risk, are interesting for practitioners because they have all sorts of very good properties that they're, you know, you can change the currency and they remain like, you know, valid. Like there's lots of nice properties of this measure, so that's why they're interesting in practice. But like, it's actually quite hard to optimize for this type of metrics. Like if I wanted to actually optimize my strategy as a store manager to optimize for the value at risk of my policy, that would actually be quite hard. And this is the topic of the talk. We're going to see how we could do this, how we can optimize a policy for the store manager that optimizes for a certain value at risk. Yes?
Are you thinking of particular parameters for the alpha?
Yeah, alpha will be given. Like you have an idea of what risk you want for your strategy. So what risk you want for your portfolio if you're trading things. Yeah. But yeah, so even for a given parameter, this is a hard quantity to optimize, especially in these complex problems that are Markov decision processes. So to not make Nicolo anxious, we're going to remove all this like amount of money and entrepreneurial, you know, entrepreneurial spirit from this talk. And, you know, maybe for the more familiar with RL problems, this is like the usual example that people have been looking at in reinforcement learning is the cliff environment. So in a cliff environment, you start from the left side here, this green dot, this green square, and there is a cliff in the middle, hence the cliffs at the beginning of the talk. So there is a cliff in the middle, and you want to find a strategy that is going to go to the other side. And obviously, there are many ways of going to the other side. Every step costs you one, you know, like you have a cost for every step you take, right? But like if you step too close to the cliff, there might be some, you know, wind that's going to push you into the cliff. And if you fall, it's like a very negative reward. So you want to get as soon as possible to the other side of the cliff, but like there are different ways of trading your risks. And essentially, if you have, you know, a very risky policy, you may like just run through like this kind of little edge between the wall and the cliff. Otherwise, you're going to take a detour. And that's for like less risky. So like this is the type of policy that we're going to try to see how we optimize using some, you know, RL techniques or actually planning techniques. There's no RL. Like in all this talk, I know my environment, I know my dynamics, I know everything, a bit like in the retail store. I tell you what's the cost of the bike. I tell you what is going to be, you know, I tell you a lot of things. You need to optimize for optimize the policy. So, okay, so these problems can be modeled by Markov decision processes. A Markov decision process is essentially a controlled Markov chain. You have a state, you can take an action, and this action is going to control how you transition to the next state. And during this transition, you observe a reward, an instantaneous reward that can also be a loss, right? It can be negative. And at the end of this process, like you're at the end of the finite horizon, typically you get a return, a total return that is the sum of the rewards. So, you know, given an initial state, so you start like in the retail store example, you start with 10 bikes typically, and you're going to be given like a discount factor that is going to control how long is your horizon, like how long ahead you need to plan, right? Like, and the goal of reinforcement learning or the goal of planning in this talk is to find a policy which is a function that maps the state to the action. So given the stock, how many bikes I have right now, what is the action, like how many bikes should I buy, right? And in general, this policy, this function, doesn't need to be stationary in the sense that like it can depend on t. Maybe if I'm week 19 of my, you know, of my pop-up bike store, I'm not going to do the same thing as if I'm week 0, right? It's maybe like, you know, if there's no tomorrow, I can take a risky action, right? Whereas if like I'm in the beginning of this game, I should be more careful, you know. There's really this notion of non-stationarity in a lot of the things that I'm going to talk about in what's coming. Okay, is the notion of policy clear for everyone? I see nods. Oh, okay, cool. So to please Gergo, I have the Bellman equations. No, actually, they are central to this work. So in control in Markov decision processes, we have a very precious tool, which are these Bellman equations. So the value function is defined as the return that you will get in expectation when you take an action and then you follow the policy for the rest of the time in your MDP. So this is like the state action value function, right? I take an action, I get the local reward R, and then I follow this policy and I get the expected return. Okay, and for the optimal Bellman equation is the key tool that is going to give us algorithms, like a very nice polynomial time algorithm to compute the optimal policy. So the optimal Bellman equation gives us a direct relationship between like the optimal value function in a certain state. I noticed that there are mistakes. The optimal value function in this certain state, and like the optimal value function in the next state. So like it really gives us like a kind of a connection between the value function in the different states, right? And so that gives us the celebrated like value iteration algorithm, typically, that allows us to compute the optimal value function in a Markov decision process in a polynomial time. So this is like, essentially you initialize the value function in every state, which is like the expected reward that you're gonna get in this state. And then you're going to iterate this recursive formula that just makes you compute the Q function for the next state, like for all the actions. So like in all the states, you iterate this process. In all the states, you compute the Q function for all the actions, right? It gives you the future value for these actions. And then you just set the value of that state to the maximum. And then, so like now all the states are updated to like what could be the optimal value if you would do the optimal thing in this, like the best thing in this state. And you're going to do this until you reach a fixed point. And this is what the nice Bellman theory of like optimizing in MDP gives us this very nice fixed point problem that gives us a polynomial time algorithm to solve these a priori very complicated problems. All right, so when you do this quickly on like a cliff environment for you know the expected reward that I just presented, like you obtain basically the optimal action in every spot that is going to guide you, you know, if you start so this is the optimal policy at state 0, but like it's actually stationary. So like it's going to give you like how you should behave, and you see you don't walk too close to the walls, and then so maybe I can point here, you don't walk too close to the walls, and then you walk a bit further away from the cliff, and then you end up in the optimal place. Okay, so.
This is for a particular gamma though, right?
This is for a particular gamma, yes. So gamma is gonna, very good transition to my next slide. So here really gamma kind of controls how far ahead I'm willing to plan and how much time, essentially how much time I have to reach the goal and how much I can spend on every step. But the problem is that this is not risk sensitive. I've been optimizing for the expectation so far, right? So we completely left away the notion of risk for this moment, so like explaining value iteration. But now I want to reintegrate the risk measures in my problem. So like Gautam was saying, like there's this gamma that controls my horizon, right? And here what I'm gonna want to optimize is actually a risk measure. So this risk measure is denoted by rho. And I can kind of equivalently write this problem down as like a discounted, you know, infinite horizon, but discounted return, or finite return like this, and I denote the return. So this now inside the parentheses here, it's the random variable, the sum of the rewards when you execute a policy, which is random, right? Because there might be random, like the stochastic transitions between the states, right? So we have this random variable, and we want to optimize, we are gonna wanna optimize the raw instead of the expectation. And I could do it for the gamma, like discounted return, just like I just explained to you. It would just make a lot of my equations a lot uglier. So I'm going to, in the rest of this talk, I'm gonna use the not so equivalent, but like kind of equivalent finite horizon setting. And it doesn't hurt me too much because as I kind of gave the intuition earlier, like the policies when you're trading risk are going to be non-stationary, right? Right you do at the end of your time is not the same as what you would have done, like what you would have done in the same state, but earlier in the time, right? Like because there is like this notion of how much time is left for you. Okay, and the notions, the risk measures that are interesting are typically like the value at risk or the conditional value at risk, or more generally like a threshold probability. Like I want to find a strategy that never falls under. That never falls under a certain revenue of like 250 euros. Like I don't want to lose more money than that. And so how can I optimize this kind of risk measures? Is the problem clear? Yes.
So pi here is deterministic policy. You're not looking at like policies that map states to distribution over actions.
It could be a priori, like why not? It could be a stochastic policies, but in the end, okay, good question. I think the policies that I'm going to optimize in the end are going to be deterministic. Okay, the question of whether this is because the optimal policy is deterministic, I'm not sure we have proved that. So I would like to claim it, but I'm not sure I can. But I think this is the case. So let's think of it as like deterministic policies. Okay, so I focus on this. And my optimization problem in this talk is going to be to maximize, to over the whole space of policies, let's say deterministic policies, maximize the risk metric that is given of the random variable of the return. Okay. Yeah, cool. So we have a tool for this. And this has been, a set of techniques that has been developed by colleagues at DeepMind and other people. That's called distributional dynamic programming. So essentially in distributional dynamic programming, you really want to, it gives you a Bellman equation, a nice tool to propagate not the value function, like not the expected value function in every state action, but the entire distribution of the return. So similarly to what we've seen before with this like Bellman equation mechanism, we define the Q distribution, which is the distribution of the future sum of the return, given a state and a given action, right? As kind of what you want to do is at a certain state, in a certain state for an action A, you want to sum the distribution of the return, the reward, sorry, at this step with the return that's upcoming, right? Which is a complex distribution that like kind of adds a bunch of things that have like a lot of randomness, right? And this sum here just for the distribution transforms into a convolution, right? So now for a given policy, I have this nice Bellman equation, like optimal Bellman equation, that's going to allow me to propagate polynomially, that because like these are infinitely, like these are very big objects, right? These are distributions, but like nicely, just it's the same way as we did before with the value iteration algorithm. You have a value iteration for these distributions. Okay, but like it's only for a fixed policy because there is no notion of like optimality. The notion of like what is the best action in a given state would have to be given by what criterion you're optimizing for this distribution. Right, so like typically, in distributional, what people do in this book, if you would read this book, they explain to you that you can propagate distributions, and then you can use this distribution to compute like notions of uncertainty and variance, and not only propagate the mean, but also the variance and things like this in an MDP, and they use it for exploration purposes. But we're going to use distributional dynamic programming for another purpose today, because our interest is to compute these raw metrics on these distributions that we have for our MDPs. And the question is, can we optimize for any statistical functional just using the distributions that we have computed and just applying rho, essentially applying rho on both sides of this inequality? So, like, or put differently, like with more visually, we have, you know, like, we want to do value iteration, but can we? For a given functional f, we would like to know whether we can compute like some sort of value function, right, that kind of computes this convolution between the reward now and the reward of the best action, like of the best next state, given that the best next state is defined as like the one that maximizes a certain metric, right, like certain raw metric. So I would like to essentially just transform my previous value iteration algorithm into one that like computes the best action for the metric f, and just have the value function for every state as like, you know, the maximum over this metric. Okay, and the question is, can we always do that? Are these equalities here, are they always true? Do we have a Bellman equation for all the metrics f out there? And in particular, do we have it for the conditional value at risk, which is the one of interest today? So we proved in an earlier paper in 2023 that this is not the case. That like in general, there actually isn't a Bellman equation for any statistical functional that you may think of. So this is a negative result. It essentially says that the only statistical functionals of the return that you can optimize via Bellman equations, for which the Bellman equation is valid, are the expectation, as we all know, and the entropic risk, which are exponential utilities that write as follows, essentially log exponential moments of this distribution for a certain parameter, for parameters beta that go like that are in R, right? Negative, positive parameter, beta parameters. And the way this result works, so I'm not going to do the proof. It's actually a short enough proof. Essentially, we prove that the only statistical functionals that you can optimize with the Bellman equations, they need to satisfy like the von Neumann-Morgenstern theorem. They need to satisfy a couple of properties that are called independence, like they should be able to be mixed with other distributions that are independent and still kind of maintain the order between the metrics, right? And you need to be able to add a reward, right? To like in the equation, maybe that's visible here. Like you need to translate it. When you translate it by a certain reward, you still need you want to maintain the order between the actions, right? Like when applying your rho function, it should maintain the order between the actions, right? So I mean, okay, this is a little bit hand-wavy, but essentially the only statistical functional that you can optimize via Bellman equations, they need to be expected utilities. So they need to take the form expectation of f of z. And then kind of looking at what this, Bellman equation imposes as constraints, we write down like a few constraints on these functions f, and we figure out that the only functions that actually validate these constraints are the linear functions and the exponential functions. So the proof is reasonably, like, it's quite short, but like this result is super strong. It essentially says if you want to have a Bellman equation, well, that's the only choice for you. Okay, so then what about the value at risk and the conditional value at risk? So because people have been doing this, it's not because it doesn't work that people have not been doing this. So there are papers for a long time. This is a topic that has been studied in finance, in particular, like in applied mathematics. What people have proposed is to augment the state. So what you do is you put the return in the state, like the sum of the rewards, right, that you've seen so far. You just put it in your current state, and that kind of makes it part of the optimization problem again, and that solves the problem. That kind of makes value iteration valid again. The problem is that then if your reward function is not discrete or something, like you may actually end up with a infinite state space, like, so that doesn't make your problem that much easier. But like, okay, this little trick makes it amenable to do like DQN and all sorts of like magic things that people have been playing around in the deep reinforcement learning community. But like other people like recently proposed to just discretize this augmented state space and try to find a nice way, like an efficient way of discretizing the state space to still optimize the metrics. So like there are techniques, right? But today what we're going to look at is actually approximation techniques. So what do you do when, you know, like, can you find a way to approximate these metrics in a way that like actually gives you tools to optimize them with the Bellman equation? And for this, we're going to a bit follow like the idea of Howe et al. That's proposed to look at the anthropic risk measure and kind of see if we can approximate the conditional value at risk with these functions. So this is going to be our process today. We're going to do dual optimization or dual search for these policies in 3 steps that I'm going to describe one step at a time. First, we're going to project into another space, this like mysterious search space, search in there, and then project back our policy into like the original metric that we were trying to optimize. Okay, so first step. How do we do this? So first, the value at risk. So we're going to consider the value at risk for this example, but it also works for conditional value at risk and other risk measures that we've mentioned earlier. But like for this example, let's have a look at what this metric actually is. So, okay, recall that the value at risk is essentially this quantile, right? And for any like random variable, the risk, like the probability that it falls below a threshold is actually bounded by Chernow's inequality. So that gives you this expected exponential moment. And if you solve this equation, if you equal alpha here, you obtain a solution for L, right? The solution for L essentially takes this nice form, 1 over beta logarithm of the exponential moment minus 1 over beta logarithm of alpha. And I'm going to call this thing AX of alpha beta. Okay, so naturally, like by definition of this AX of alpha beta, we have that the probability of X smaller than this threshold is actually smaller than alpha, right? And then, so indeed, like this thing is smaller than the value at risk. So we've just found that like this kind of function here, it gives us an approximation of the value at risk. It's actually not so bad of an approximation of, yes. So, okay, and so now if we want to, optimize for, like find something that's close to the value at risk, we can just optimize on beta. So on this variable beta, we can just optimize this function that gives us something close to the value at risk. And this function here, so this function that is in green, was studied, like it was defined and studied by Ahmadi-Javid in 2012. It's a big paper that defines what is called the entropic value at risk as an approximation of the value at risk, and then just kind of studies all the approximation quality with the CVAR and the VAR, etc. So like there's a lot of work on this particular function. But for us, it's particularly interesting because this function here looks really much like the one that we can actually optimize by dynamic programming, the one from the theorem that we had earlier, right? So essentially, we transformed our problem in an entropic risk minimization problem, right? Where now we can search for the policy pi beta that optimizes for this function instead of the value at risk and hope that it gets something close enough to the actual metric we're looking for. Okay, so we've now transformed our problem into something that's tractable where we can optimize. The question is how we're going to search in this space, because now we haven't made our problem so much easier because we have infinitely many values of beta, right? We need to search for every policy, for a fixed beta. By dynamic programming, I can find pi star of beta. So this is okay. Like polynomial time, easy, I can find a pi star of beta. But I have infinitely many betas. So how do I do? So what people did, this is how et al. 2023, they proposed a smart grid search. So they cut the beta space into plenty of little bins, and they compute for each of them, they compute the optimal policy. And at the end, they return all of them, and they find one that's like they just optimize on this finite set of policies. Okay, so that's an approach, I guess. But maybe we can do a little bit better. And we're going to see how. So let's assume we're in a city that is not Milan, because the pizza is terrible, and the fish is most of the time terrible. So essentially, we have two restaurants with two distributions. And this kind of models is a very simple decision problem, where the question is, what restaurant what do you want to choose? Like, are you kind of the YOLO manager? You want to risk and get potentially the good fish, but maybe not the good fish, or do you want to just be sure and most of the time get an okay pizza? Okay, so I did the computation for you. You have a utility function that depends on beta. So this utility function that is like this exponential utility gives you a formula that you can plot. So I also plotted this for you. So I have a nice kind of sigmoid style kind of utility function that tells me that, like, for low values of beta, I don't like so much my pizza, and for higher values of beta, I like the pizza. But like then the interesting bit is to do it as well for the fish. So I do the exact same thing for the fish for this distribution that's over there, and I have essentially two of these sigmoids, right? And these sigmoids, they tell me what is the optimal action. Like for every beta, it tells me what is the restaurant I prefer according to my utility function, right? So if I have a very low beta, I still prefer the pizza. It's not great, right? But I still prefer it. There is a threshold, this breakpoint, and after this breakpoint, I start preferring the fish. So when beta is large, I like extreme values, even if they're rare, right? And so I will favor the pizza. But essentially, in this problem, that's very simple decision problem, there are only two optimal policies. There is an infinitely many, there's a continuum of betas, there's a breakpoint, and there are two optimal policies. So it's very structured in a way, like I don't need to compute all the optimal policies for all the betas. I would like to have a way to just find the breakpoint. And then, it's easy, right? Once I have the breakpoints, I can just find the optimal policy on each side of the interval. So the question is, how do I find the breakpoints? We proved that the optimal policies is always piecewise constant, right? On this, like for values of beta, we have piecewise constant policies. And we're going to call the optimality front the finite sets of optimal policies and their according breakpoints, right? So I'm going to structure the set of policies like according to the values of beta in like this set that's going to be called the optimality front. And like how et al., the first idea is to search for, discretize the space of the beta, find the breakpoint, and then that's it. Once I find a breakpoint, I'm good. Okay, so that's one way, but it's not super efficient. So our new result is actually to look at these utility functions and say, look, they're not arbitrary functions. They're nice exponentials. They have like a nice smoothness, right? So when you are like in a state S, right, and you look at the actions that are available to you, you can compute essentially an optimality gap. Like how far are you, like how bad is the pizza compared to the fish at this moment, right? Or how bad is the fish compared to the pizza? So literally, how much time in beta time, like how many beta values do I have in front of me before there's a breakpoint? So we define this kind of generalized advantage function, which is the difference between like the entropic risk and the entropic risk when you take the action A, and then this gives rise to this kind of this optimality gap that I just, describe about the pizza and the fish. And essentially what we prove is that for a given optimality gap delta, there is an interval around your value beta for which you know that the optimal policy is stationary. So like there's no point for you searching, like looking at the values of beta in this interval. So that's a very natural algorithm. You start with a certain value, typically you start with 0, and you're gonna move beta up by jumping. You jump the values of delta that you compute. And you can compute these values because you know your MDP, you know everything in there. So you compute these values, you jump ahead, and like this, you jump values of betas, and you only get like these deltas, they actually only get close, they get small when you're close to a breakpoint. So you're gonna make big jump when you're far away from a breakpoint, and at some point, you start jumping very small, like slowly to the breakpoint and up to a limit, a limit precision that you impose to yourself. Right? And that gives this. So like this is the pizza fish example, right? I'm zooming here on like around the breakpoint. And sorry, it's a little bit small, but I think you'll see. So these are the beta we compute. And this is the fine grid that corresponds to the precision that you impose to your system. Yes?
Are you guaranteed there's always a finite number of breakpoints?
Yes, you're guaranteed that there's a finite number of breakpoints, but you do not know how many. And like we don't know how many. There might be a way to get an upper bound on the number of breakpoints, but we haven't found a way to do this.
So the finiteness is guaranteed.
Yeah.
So if you only have one breakpoint, let's say, so this and that, and would this be comparable to doing binary search, or would it outperform it in some way?
Yes. So the question is, so the problem is you never know if you have only one breakpoint. So if you know, sure, but you never know, and there can always be crossings. So sometimes, you're here, you see that like the pizza is better, then you're there and you see the pizza is better, you cannot conclude that there's no crossing in the middle. So that's the problem. Yes?
Are you trying to compute all the breakpoints? You may never stop, right? Like, it can be finite, but larger than how much computation you have, right? So how do you...
Sure.
Stop prematurely, like you just stop at time?
I mean, okay, that is true in principle because I don't have an upper bound on the number of breakpoints. I think, okay, in general, you're right. There could be a lot of them and like, you're not gonna be great, but it's better than like, so the cases where your remark is particularly true is in very big MDPs, very large state, very stately, things like this. In that case, the discretization is also not so great. So, yeah. Yeah.
How do you, if there are multiple breakpoints, how do you move beyond the breakpoint? Because as you approach it, you slow down.
Yeah.
You never get over it. So how do you get to the other side?
Yes. So at some point when you get too close, you have a limit precision, right? So you're going to say, okay, I know that the delta is so small that I know that I'm that close to a breakpoint. So then you decide this is your breakpoint. You jump ahead. You do like twice the interval or something, and then you're on the other side, and then you start jumping again. Yeah. And also what I've hidden is that you start at 0 and you go up, and then what you do is you start at 0 again and you go down. Like you're gonna do, the 0 is a bit of an edge case, like because in 0, these exponential utilities that don't behave so well. So like essentially like they're equivalent to expectation at beta equals 0. And so like the breakpoint, our techniques is gonna give us infinitely small intervals. So like we start at 0, we go up, and then we do the same thing, we go down. Yes?
So I guess, could you like help me sort of relate, I guess, like beta, like the beta, the policy is optimal for a certain beta back to our original objective. And in particular, I'm wondering, like, does it matter that we sort of find all the different policies, or as long as we find like the right policy corresponding to sort of the right beta, then whichever side of the breakpoint we're on, that will still have good performance for the metric that we care about.
So the problem is you don't know what beta you care about. For the moment, like you're trying to do this, like, yes, you're trying to maximize over beta, right? So you don't know what beta you're looking for, right? So the idea is to find them all, like to just map what are the optimal policies for all the betas. And once you've mapped them, then you know which one has the, like, is going to have the larger value for the metric that you care about. This is going to become a little bit clearer once I go through like the third step. So bear with me for a second, but I see there is a bit of a, right now I'm making a detour to explain to you what is the structure of this not so mysterious dual search space. And then we see that this structure actually helps you solve the problem a lot. Other questions? Okay, then let's move on. Cool. So essentially, yeah, I've structured this search space into like kind of discretized, like there are optimized policies like this, and there are breakpoints, and I have a way to find them. This way is not optimal in any way. Like I don't know if there are better ways to search for these breakpoints. We actually search for other ways. I could discuss that later, but like generally, like there are no. It's hard to find these breakpoints, and discretizing is not the smartest thing you can do, and maybe the jumps are not the smartest thing either. But then the question is, how do you go from this one-state problem, the pizza fish problem, to an MDP, right? Because it seems like in an MDP, once you found a breakpoint for a state, then there is another state. Like, how is this going to, like, how are the breakpoints going to kind of combine each other? So that was like, we needed to prove first that, like, when you found the breakpoint for a state, essentially these breakpoints, they combine. They are also breakpoints for the states before, right? So if you're here, right? You're next to the cliff. There are 3 actions, or there's actually a 4th one, but the utility is not super interesting. So like there are 3 actions, and I plot their utilities. And for safe betas, you go left. For middle betas, you go up. And you're gonna go like this. And for high betas, you go through the edge, right? So like you have your utility function, and as for each of these betas, you have your optimal policies. So there are only 3 objects to store. But then, like, once you do one step backward in your iteration, in your value iteration, then you have to consider right now that if you do the step right, there's going to be 3 breakpoints. And so what we prove by this like nice recurrence kind of like recurrence relationship, like the breakpoints for the next state are also my breakpoints at my state right now. So through this recurrence, I actually have a very nice way of kind of computing the breakpoints in like backwards in my MDP. So we're gonna see how that like recursively in the same way as compute my the optimal policies for the criterion. So like the way it works is that like I'm gonna first consider the negative betas. Right? Actually, it's the only really interesting one because we're optimizing over beta negative, right? So here I consider all the interval for like minimum value of beta 2, 0. Okay, minimum value, we have ways to compute what could be a minimum value for beta. I don't detail this, but in general, you could also say I have a cutoff, right? At -10, that's fine, So you have your minimum value, and you start there, your iteration. And you're going to start doing the jump, but you start at like the last step of your MDP, at h equals capital H, like at the last time, and you compute the breakpoint for all the states of your MDP, right? So you compute for each state, you do this little maneuver of looking at the jumps and like finding the breakpoints and the optimal policies. Then you do one step before, and for all the states, you already know what are the pre-breakpoints. So you can consider each of these intervals independently. So you're going to do the maneuver of like computing the breakpoints, but within these kind of sub-intervals that are defined by the next states. And you're going to find again, you're going to partition this space into sub-intervals, and you're going to do this like this until you reach 1. I know it's not super, super visual, but like essentially you can do the same procedure many, many times. And the nice thing is that every state is independent. Like you can do this in parallel over the states, right? Because you just compute the utilities just like I showed you when you do your jumps. So that's a relatively efficient kind of computation. And for the more visual people, what you obtain is actually for a very simple cliff environment, what we obtain is something like this. So here, I know it's a little bit overwhelming to look at, but so this is the color code as the beta parameter. And we color the arrow as like the first beta for which this becomes optimal. So like typically, this state here You know, even for a very safe policy, like, you know, there's only one good action. So that's okay. Okay. But so for this state here, the safe action is to go up. But once you reach beta is like, this beta is a little bit like greenish, right? You're somewhere around here. The optimal action becomes to go around this, you know, the cliff like this. And then you finish your policy. So essentially, like the number of colors and arrows that you see are the number of optimal policy for all the continuum values of beta that I'm looking at. So I don't have that many in the end, right? I've really kind of like, from an infinitely many values of beta, I've boiled it down to like just a few optimal policies. Okay, is that like roughly clear? The whole mechanism of the breakpoints and everything? Yeah, I know it's a lot, yes.
Maybe I was wondering, so you said you had this proposition saying like the breakpoint for the next state, the breakpoint for the state, but does that mean like, but there could be more breakpoints for the current state? Or?
Yeah, exactly. So the current state is going to split again. Every single subinterval is the current state. When you do your jumps, you're going to find more breakpoints, potentially. I mean, not always, like some of these like states, you know, they never change, right? There's on essentially no breakpoints. But like you're going to subdivide the new interval into subintervals, and then when you go to the next, you know, h-1, then you're going to have to look at these subdivided things. But the truth is there are not that many breakpoints. Like most of the time, as you can see, like there's one or there's two, but like there's really not that many. There was a half question.
Yeah, I was just worried that like the breakpoints are increasing. Like if the current state's breakpoints contain the previous state's breakpoints always, then it's like increasing.
Yeah, it's increasing. Yeah, there's more breakpoints. Yeah, there's more breakpoints in the original. You know, at time 0, there are like a lot more different optimal actions, and like when you're at time h, like and essentially, like there's nothing else you can do, right? Yes, I did. I'm assuming finite state space, and I'm not sure how this would go through like infinite state spaces. Yeah.
So what actually do you mean by the next state? The multiple state?
Yes. So like basically when you're taking an action, there are multiple states, and they're going to define the value of this action kind of thing, right? So like each of these next states, they have their own breakpoints. So you need to consider like the different subintervals for each of these, like the value of these next states kind of thing. Yes. Yeah, it's conditional on the action. Yeah. Okay, so now we have our whole optimization procedure. We have our original problem. We transform it into an optimization over beta. We realize that this optimization over beta is actually not that hard. I mean, it does ask us to compute a bunch of things, but these things can be computed relatively efficiently, right? We obtain a set of policies, so a set of breakpoints, and a finite set of optimal policies for these betas. And then what we can do is just look at this set of policies, like all these pi star of beta, and just compute our C-var for these policies. Like this is okay, right? For a given policy, I do have a distribution, like I can compute the distributional return. Like this is distributional dynamic programming. So I have the distribution of the return for this policy, and I can just compute the C-var of this distribution. That's fine. So through the distributional dynamic programming, I have now just a finite optimization problem on a finite set and a small enough set of optimal policies, and I can just like maximize the C-var on this set. So yeah, we're reaching the end. You know, essentially the take-home message of this paper is that like this optimization of certain risk metrics that are tail-based risk metrics, probability of threshold, C-var, var, etc. They can be posed, like they can be computed as like some optimization over an easier set of metric. You know, we show that like, you know, this thing can be done efficiently, and we actually do it in practice on small examples. We still have a few open problems though. Like typically I haven't said anything about the quality of the approximation that I'm getting. Like I'm going to compute this one, like this one. How good it is, I am not so sure. And I think this is actually a really hard problem. I'm not sure how we can even start to tackle this. There's also, like we've always assumed, finite state action spaces. Also, really, it would be really cool to find a way to extend this to infinite, like kind of structured action spaces. And so far, no learning. I've essentially done the planning, I've done the optimization, but if you don't know the model and how you optimize, how you do RL essentially, how you optimize for risk metrics, if you don't know the model, that seems also like really hard. I'm not exactly sure how to get there. There's literature. It's an interesting, like it's a big problem. There's actually more people than I thought working on this. When we started, we thought we were a bit alone looking at our little thing, but we're not. There's a lot of people, and especially we find a lot of people from these Boyle, Nicole Boyle in the Karlsruhe Institute of Technology. She's an applied mathematician, but she really works on exactly these kind of topics. Not really RL, but optimization in MDPs. So there's quite a bit of resources from the mathematics literature, and yeah, it's a rich problem with a lot of open questions out there. So yeah, I'm happy if I have made you excited about the problem as well, and I'm happy to also answer your questions.
Claire, we can take questions.
There's Mark over there. Yes.
Thanks a lot for the talk. So you mentioned the fact that the policy that you're looking for are maybe not stationary. Of course, if you are finite horizon, okay, but I don't really see why it would be the case for the discounted setup, because although the subroutine that you saw with the one for the class of computer is not limited.
Yes. So the problem of the discounted setting, I'm so happy I made this extra slide. So, okay, thank you for the question. So, yes, so the problem of the discounted setting is it's also a finite horizon setting, right? It's just parameterized a bit differently. And the problem is that when you optimize on like your beta, when you want to optimize this beta policy, at every step every step t, of your process, you're basically going to have to rescale beta. So for the Bellman equation to be correct, you need to rescale the beta that you're considering by 1 over gamma. Like so you rescale beta by gamma at every step in the thing. So like you're actually not optimizing the same beta at every step of your MDP. So that's where the non-stationarity is going to come from. It's just when you write down the Bellman equation, there's a beta. And this is actually not, it's known for a long time. So when we started working on this, we thought that like we were, that we didn't know anything about exponential utilities in MDPs, but there's a Borka paper in 2002 and another follow-up in 2010. So Vivek Borka is a control theorist in India, and he already proved that you can do value iteration for exponential utilities in the discounted setting by rescaling. And then in 2010, he actually explained that that leads to a Q-learning, and he proved the convergence of Q-learning. So essentially, when we had our original result, like the theorem that says that you can only optimize this, essentially it closed the loop. Like there's nothing else you can do, and we already know how to do it. So like there's no more questions left, except that like okay, you can do this, but there is all the questions are left, right? Like what can we do with the other metrics? But yeah, that's in the discounted setting, the problem is that you have to rescale at every step.
Cool. Other questions? See.
So in this setting, you apply rho to the entire cumulative reward, right? But like there could be settings where you actually care about having some rho constraint on each individual row at every time point. Do you know if there's any work on that?
So Peter Dayan is interested in this. So I am not sure how, like, I haven't looked in the math of it, because Peter Dayan and like his team, like in neuroscience, they're super interested in this to model human behavior and like risk averseness in human psychology, and they do have some empirical results, and they try to kind of extend some of the value iteration. The thing is, what they often do, you know, they use approximate Bellman iteration, saying it's not correct, but it's almost correct, or in certain cases it's correct, and then they compute optimal policies, and it's good enough for some of the settings that they have, but like they haven't, to the best of my knowledge, they haven't really solved the question of like, you know, solving the math problem, the control problem for a changing, typically like a changing risk measure, or like a different way of, you know, how you would, you know, maybe you care more about the CVAR alpha at the beginning and maybe CVAR 2 alpha at some point, something like this. They look at these kind of things, you know, to model resilience in like diets kind of things, or, you know, other type of psychological phenomena. But like Peter Dayan has quite a bit of papers on the topic with yeah, really cool results as well.
Thank you. Other questions? Gergely?
All right, thank you for the very nice talk, and the Bellman equations especially. But so you said that the only utility that can be optimized is this exponential utility if you consider dynamic programming algorithms. But dynamic programming is not the only way to solve Markov decision processes. In particular, you can solve them by linear programming as well. Mm-hmm. So does that approach apply to this setup, or does this negative result apply to linear programming approaches as well?
Yeah. So that's a good question. Actually, it's the first remark that Emily Kaufman made to us in like our EWRL poster like back in 2023, and we were like, sure, she's right, but okay, that's a hard question. Okay, so I don't think it applies.
Yeah.
I think
I agree.
you can optimize a lot of other things in this linear program kind of setting. And people have done like this like convex RL and regularized RL that you're more than aware of. Yeah. And I think it's just I'm struggling to really connect these two dots and wrap my head around. Like, yeah, at some point there's still like in this linear program formulation you have the constraints on the Markov flow, right? You still have to have that. I think you would keep that. But like a lot of the metrics that people are optimizing in these problems are actually not reward related. Like, you know, they're going to optimize the entropy, or like optimize the reward, the expected reward, regularize with like the entropy of the policy or things like this. And there's no reward in there. So I don't know if like how it connects to like having these risk measures of the reward. I'm not sure. Like, this is a good question. I've tried to think about it, but I don't have a good answer for you. Yeah.
I know I share a lot of those sentiments. I do think that maybe this LP approach is not really suitable. Right.
Yeah.
Okay.
It's yeah. I don't know.
Right. Okay. Thank you.
But maybe algorithmically speaking, it could also lead to things like, you know, maybe there are ways of making things more tractable, especially maybe in infinite state action spaces. Maybe it could. Yeah. I don't know. We could think about it.
Other folks? I had a question myself about, can you go back to this slide where you use the Chernoff inequality?
Yes.
I had two questions about that. Yeah, first of all, it says for any beta less than 0, but I saw you using both beta greater than and less than 0 later on.
Yes, that was for, okay. So for this paper, optimizing for CVAR alpha, the only interesting values of beta are the negative ones. Okay. Because this problem, essentially via Chernoff, you only get this problem over negative values.
I see.
But then, okay, I did a detour to study like this problem typically where a positive value would also be interesting because, you know, they also model kind of risk, you know, like risky behavior and things like this.
Gotcha. The second thing about this is that it's an inequality. So, like, do you know how tight or loose this might be?
So, yeah, this is the big, this is the $1,000 question, maybe more. I don't know. So, the problem is it relates to this open problem, this quality of this approximation.
Yeah.
I've made an inequality. This is Ahmadinejad. I haven't done anything. He did it in 2012, and he does study, the relationship between this EVAR, this entropic value at risk, and the CVAR and the VAR, and basically the EVAR is like kind of in the middle. And you can, for certain MDPs, you can plot it. You can see like how loose, how tight it is. Essentially, hand-wavingly, it's tighter if you have rich reward. So if you have like kind of a like heavy tail distribution, complex reward, complex return function with like heavy tails, it's gonna be. Oh wait, what am I saying? It's the opposite. Yeah, it's so yeah. This type of like the Chernoff like when the Chernoff is tighter, you get slightly tighter approximation. But if it's not, so if you have sparse reward, if your MDP doesn't have a lot of rewards, then the augmented state space is actually quite a good idea, right? Because like, this is the other approximation strategy. So I'm just going back a bit further, right? So like the other thing that people do is to just say put the sum of the return in your state space. But if you have very few return like reward value and like your return is kind of essentially always constant and it takes just a few values, then this augmented state space strategy actually works. You can just do this. But if you have a rich MDP with a lot of reward and like you get small rewards here and a lot of reward there, like this is going to make this approach really intractable, and then you want something else. But there are alternatives, but like the quality of the approximation is a big question.
Gotcha. Anyone else? Cool. Let's thank Claire one more time then.